Hi everyone, my name is Xuantian Miao, a PhD candidate from Swinburne University of Technology. Today, I'd like to present our paper titled The Audio Auditor User-Level Membership Inference in Internet of Things Voice Service. We'd like to thank the precious suggestions from this paper's reviewers, chairs, and the shepherd, which greatly improve this paper's quality. Now, allow me to elaborate this research step by step. For your information, this is today's roadmap. In this research, we focus on the core components of OLT voice service, automatic speech recognition system, in short, ASR system. Briefly, we design an audio auditor to perform user-level membership inference task. The auditor can verify whether a specific user had unwillingly contributed audio used to train an ASR model, especially when the transcription is the only output. The story begins that voice servers are emerged increasingly, especially in IoT devices, like Google Assistant, Amazon Alexa, and etc. However, with lots of news reported the unauthorized use of users' audio recordings, people start to worry about it from privacy and security concerns, like what BBC reported that HMRC forced to delete 5 million voice files, and GDPR law have been enforced to regulate personal data processing. Till here, we concern, is there any tools to check the regular data preprocessing, especially the information hidden from the model itself? For instance, when a user intends to cancel the account of a voice service, expect erasing the records stored in the database. Is the model behind still remember this user or not? Is it in line with the right to be forgotten regulation in GDPR law? Firstly, we unfold ASR systems behind the voice service. There are two state-of-art pipelines used to build the ASR system, including the typical hybrid ASR systems and end-to-end ASR systems. A hybrid ASR system is composed of a preprocessing step, an acoustic model training step, and a decoding step with the help of a language model to output the transcription of an input audio. It is the acoustic model that learns the audio information from its training dataset. An end-to-end ASR system mainly refers to an attention-based encoder-decoder models. Unlike the hybrid ASR system, the model predicts subword sequences, which are converted directly as word sequences. As we understand our target model, now we explore some possible solutions. Membership inference attack, in short MIA, was firstly introduced by Shakri et al. It can infer whether a record was once used to train a target model or not under the black box access. The reason is that there's always an overfitting issue within an ML model. The model will behave better in predicting a record it knows before than a record it never seen. The MIA aims to learn this kind of different behaviors to distinguish the record level membership. Specifically, Shakri et al. Used shadow models to learn the target model's prediction behavior with a few assumptions like knowing the training set's distribution, the target model structure, and the output contains the label and its confidential scores. Then, Liu et al. And Hayes et al. Utilized generative adversarial networks to generate more accurate shadow models, while Salim et al. Relaxed the first two assumptions. Further, Sun and Schematical performs user-level MIA against the text generative models. Instead of knowing the confidential score, they rely on several top-ranked predictions to infer their membership. However, in our case, We need an auditor to help users to determine their user-level membership of an ASR model, while only one final transcription without confidential score is the output. Additionally, because the characteristic of the voice, we can't expect users to replay all of their past recordings when they want to audit an ASR system. Therefore, we defined our user-level membership as this: querying with a user's data. If this user has any data within target model's training set, even if the query data are not members of the training set, this user is the user-level member of this training set. So far, you can sense that how challenging is this task on ASR systems in the real world. Since ASR systems in real world provide only one transcription without any confidence score, the lack of the information is our first challenge. Secondly, the user-level inference requires a higher level of robustness than the record-level inference, especially for the audio recordings. The third challenge brings from the ASR model itself. Its complexities in the learning architectures results in computationally resource and time-consuming. Before we move on to the methodology, we clearly define the problems wanted to be solved here. Behind the IoT voice service is an ASR model like this, trained by a set of audio recordings. When a user queries this model with an audio, under the black box access in real world, the only output is the final predicted transcription. Our audio auditor aims to help users to determine whether an IoT voice service still obtains their audio recordings as training set or not. Instead of discussing a specific model's membership, our auditor aims to distinguish this user's membership. That means a user can still find out if he has audio recordings in that training set, even querying with the audio that the model never seen before. Because users can be expected to replay all of their past recordings in the real world with black box access. For our audio auditor, the user-level membership inference is more meaningful and practical than the record-level membership inference. Here is our methodology. There are two processes. The training process is to build our audio auditor, while the auditing process is to use this auditor and gain our user-level membership result. During the training process, shadow models are trained with different datasets to mimic the target model's behavior. Then we collected those shadow models' different behaviors on their own training and testing samples in user level. Our auditor learned this kind of behavior and hope the target model shared a similar behavior on that, which help us determine its training set's user level membership. Specifically, with the feature extraction and some statistical analysis in user level, our auditor's training set is prepared. Herein, the record processed from the querying result of the shadow model's training set is labeled as member. Otherwise, the processed record is labeled as non-member. According to previous study, when shadow models' architecture are the same, there are no big difference in the performances between using one shadow model and using multiple shadow models. Thus, we only train one shadow model for each model architecture. To differentiate the auditor trained with different settings of the shadow model, we use the combined auditor, inferring the settings of using multiple shadow models. As for the auditing process, firstly, a user queries the target model with their audio. With the same feature preprocess, the record will be fed into the auditor, while the output is either member or non-member. To achieve user levels determination, the feature extraction in the training process is the most important part. We firstly extract two kinds of features: the audio-specific feature like speed and frame length, and model behavior-specific features like similarity score, missing characters, and extra characters. Herein, Glove model is used to measure the similarity score between the transcriptions and the true text. Here is an example about the missing characters in brown and the extra characters in green. With some feature process in user level like statistical analysis, we discussed the effect of different features. Here we find that the missing characters and extra characters can enhance the ability of our auditor, while the performance is not improved when considering the additional MFCC information. Therefore, we use the feature set 5 in feature extraction to build our auditor. To be noticed, since our auditor is the first work investigating the user level membership in ASR system, the comparable baseline is considered as 50% in accuracy. Briefly, we evaluate our audio auditor from 4 perspectives, including effectiveness, efficiency, data transferability, and robustness. To test the auditor's effectiveness, we evaluate whether users are feasible to use this auditor with acceptable performance, especially in real world. For efficiency, we evaluate under what condition the auditor can perform the best. For data transferability, we evaluate the effect on the auditor's performance when it was trained with different data distributions. And for robustness, we evaluate the effect on the auditor's performance when it was trained with different architectures or in a noisy environment. Part of the results are shown in today's presentation. These two figures show that our auditor still effectively discriminates the user level membership with only a limited number of audios used per user. From figure 3, on a smaller number of users in the auditor's training set, we observe a rapid increase in performance with an increasing number of users. Assume a user is one user level member of an ASR model. From figure 4, we know that the auditor can perform a much higher accuracy using the recordings that the ASR model seen before than using that unseen recordings. Specifically, it has a peak accuracy of around 94%. In conclude, it's better for users to choose the audios once heard by the model. The auditor audits target ASR models trained with different data distributions. We observe that for accuracy and recall, the target model with the same distribution as the auditor performs the best. In general, the data transferability is well observed with reasonably high metrics for all data distributions. In this table, the target model is LSTM-based ASR model. However, the auditor with the LSTM-based ASR shadow model is not the best. Instead, the auditor with GRU-based ASR shadow model shows the best result. In fact, we can observe from the table, although they have different architectures, their overfitting level are the most similar one. We can conclude that the best is the shadow model shares a similar overfitting level as the target model, and when the overfitting level is unknown, the combined auditor can achieve accuracy higher than the average with small set. To test our model in the real world, we keep our auditor model locally and conduct a proof of concept trial to audit iPhone series speech-to-text service. According to series statements, I can be considered as a member user of my iPhone series ASR model since I choose opt-in option to improve Siri and dictation. As stated by iPhone series privacy policy, users' data can be retained for up to 2 years. Thus, another 52 non-member users were selected randomly from LibreSpeech dataset whose samples were collected before 2014. To gain the average performance of our auditor in the real world, we store 100 auditors under the same setting with the training set conducted 100 times. The average overall accuracy is around 90%, while ORC AUC score is around 73%. Further, we'd like to discuss the threats to our auditor's fidelity. First of all is voice prints anonymization. The speaker's voice can be disguised by using robust voice conversation while ensuring the correctness of speech content recognition. It might affect our auditor's performance. Second is differentially private recognition systems. Differential privacy is one of the most popular methods to prevent ML model from leaking any training data information. In ASR, it might influence the transcription's confidential score. Considering our auditor is not relying on this information, its performance remains unknown. Third one is workarounds and countermeasures like dropout generally change the target model's output probability. However, the change to probabilities of the ASR model's output are not as sensitive as change to its translated text. To conclude, we propose the use of user-level membership inference for auditing. Our auditor is effective, has promising data transferability, and is robust to various architectures and pipelines. Thanks for your time. The related code and toolkits are published in this GitHub. Feel free to explore it. And any questions are welcome to discuss.